Okay. So good evening, all of you. Let me start today's lecture.
Good evening, sir.
Good evening.
Good evening, sir.
Can you see the slides?
Excuse me, sir.
Bolo.
Sir, I have one doubt. Sir,
Bolo.
like you said that if we have different frequencies, then sir, we do this different frequency because so that the waves do not interfere in the channel. But sir, even if the frequency is different, the waves do interfere. So why we say this that they do not interfere?
They will. How will they interfere?
Sir,
Yes.
the amplitude will be in the
Huh?
net resultant of the all waves. So they are interfering.
Need resultant due to what?
So like if we pass two waves have
Uh,
maybe having different amplitude, frequency, etc., they will
uh,
interfere, sir.
why? No, they don't interfere. They will not interfere. This frequencies, they will be always propagating in two different uh, wavelengths, no? Two different frequencies. So they don't mix up. The radio frequencies, they don't mix up. That is the beauty of this electromagnetic waves, no? So they don't mix up. Until and unless you deliberately use some circuit to mix them up. Okay? They will not mix up. So you can select out. You can select out a particular frequency. That is possible. Okay. So all in all the media means that is what it means. All around you actually you have lot of frequencies now. Even where you are sitting, nah, there itself there are many frequencies are there. Means there are electromagnetic waves with different frequencies are already there around you. But when you are talking to someone over a mobile phone, that time your mobile phone is basically picking up a particular frequency. Okay, that is happening all the time. It is happening like that. Okay, they will not only they will make if they have the same frequency, then only they will interfere. That crosstalk will be there only if they are of the same frequency. So that's why the problem is that when two users are using the same medium, but if they are sending at their voice, whatever the voice frequency, say up to 20 kilohertz, that is the audio frequency. If I am using that frequency, then there is the problem because I am using the same frequency, the other person is also using the same frequency. Then there is the problem. Okay, otherwise there will be no problem. Okay, that will always, the two frequencies will be always, they will be separated out. That happens everywhere. Even in any conductor also when the signal is passing, it's like that. Until and unless you have a particular device in which they are mixed up. Okay, that we'll talk now. Today we'll talk about that. How we are mixing up two signals of two frequencies, and the circuit that will do that, that is called a mixer. That's why it's called a mixer. It mixes two frequencies. Okay, so that we'll talk today. Okay, is it clear?
Sir, I was saying that like if the two waves are having frequency, like the equation is given by sine k1x omega 1t plus k2x omega 2t. So
Uh,
by principle of superposition, the net electric field at that point will be.
Superposition, no. By superposition will they, what will be the resultant mathematically? Suppose I have sine theta 1 and sine theta 2 plus
Yes, sir.
sine theta 1 plus sine theta 2. How will you write it? What will be the resultant due to superposition? Can you write it as something else?
So we can use sine c plus sine d.
Huh?
We can use our sine c plus sine d, and there will be
Sine
different
c plus
components of
sine d
frequency.
what? What you can do? It is plus only sine theta 1 plus sine theta 2. What can you do? How can you separate it out? Only when you multiply, then only you will be having the problem. You see, if it is sine theta 1 into sine theta 2, then it will be a problem. Then you have theta 1 minus theta 2, theta 1 plus theta 2. Isn't it?
Yes, sir.
What is the trigonometric relation? Only when they multiply, then there is the problem. Isn't it?
Okay, sir.
You just see, mathematically you cannot have any other form. Sin theta 1 plus sin theta 2. Superposition is linear form only. It is just plus plus, that's all. You cannot have anything else. Only when they multiply, then it is a problem, because multiplication is non-linear. Okay, and that is what actually today we'll be saying that. Okay.
Yes, sir.
Sure. Uh, okay. Can you see the slides now? Okay, so last class we were discussing about these things, the frequency division multiplexing, and what we said, this is what the problem was, that if three users are there having the same frequency range, that is, say their speech signal, or speech signal is generally from 0 hertz to 3.4 kilohertz. So if three people are talking and they want to communicate over the same channel, then there will be the interference. So what we are doing, so that multiple users can use the same channel, what we are doing, that we are translating this to different frequencies like this, okay, by some method, and then we are pushing them in the same channel. Okay, so this is what frequency division multiplexing is. So how we do this? This is the question now, how we do this frequency translation. The process that we use for doing this frequency translation is called modulation. Okay, this is modulation. So the basic purpose of modulation is to translate baseband. We call it baseband, that is the low frequency message signal. As I have already shown here, this is the baseband. It is from 0 to 3.4 kilohertz, something like that. Okay. So this side, actually we are drawing the negative side, as I might have mentioned earlier, that this is just for mathematical representation. Okay. Otherwise there is nothing, physically there is no negative frequency. It is just the mathematical representation, that we can always write a signal in the form of positive frequency and negative frequency. Okay, so that is you'll study about all these things later on, that how whenever we do mathematical analysis, we write it in positive and negative frequency, just for the purpose of mathematical analysis, and accordingly we also sketch it accordingly. Anyway, so basically a low frequency message signal, that is called a baseband message signal, is translated to high frequency by using a process called modulation. So first we'll see what is amplitude modulation process. We'll not talk about many other modulation processes. There's many other. So we'll just talk about two basic modulation schemes. One is the amplitude modulation. The other one is the frequency modulation. Although frequency modulation also, we will not talk much about it. We'll just give a basic idea about it. Okay. So suppose I have a single tone message. Single tone means only one frequency is there. Although message signal cannot be in general like that. Okay, message signal, for example, when I am talking, my voice is having all the frequencies from 0 to 3.4 kilohertz. So it is a mix of many frequencies. Okay, so it is the addition of many sinusoids, okay, of frequencies 0 to 3.4 kilohertz. Okay, that is my voice. But anyway, for mathematical simplicity, for understanding the things, we start with a message signal, which is a single tone, single frequency. Okay, so suppose my message is something like this. AM is the amplitude, cos 2 pi FMT, that is the frequency of my message signal, single tone message signal, and there is some arbitrary phase phi. Okay, why I am using this phi? Because since I am writing it in the form of cos, but the signal may not be exactly a cosine, it may be sine. If it is sine, then phi is 90 degree. Okay, if it is pure cosine, then it is phi is 0 degree, like that. So just to take care of anything like that. Okay, that's why I'm just putting one phi. Okay, some arbitrary phi. So my message signal, I'm writing it in this form. Okay, now I have one carrier signal. This is generated by a local oscillator. I'll talk about this local oscillator afterwards. Let's talk about this. I'll just mention about it. So there is some oscillator. Oscillator are actually electronic devices that generates different signals, sinusoidal signals. Okay, these are electronic devices. They can produce signals. So that is how signals can be generated in an electronic system. Okay. So actually, it's, for example, oscillator, you have in your computer itself, you have an oscillator which generates a clock. Okay, that oscillator generates a clock at some frequency, and that clock is driving your computer. You know your computer is having some clock frequency, some speed, clock speed. So that clock is in your computer generated by an oscillator. Your watch, digital watch, that also has one oscillator in it. Okay, so like that, oscillator is something like that which generates frequencies, signals of some frequency. So I have one oscillator, and that oscillator is generating a carrier signal which I am writing as AC cos 2 pi fct. So now I am multiplying it. This is where actually the frequency can change. That is what just now I should say, that only when two sinusoids of different frequencies are multiplied, then you will be having some change in the frequency. Okay, what is the product? When I multiply them, this is the product. Okay, mathematically you know this is the trigonometric relation. You will be having this. Okay, this will be the product ST. Now here you can see, now I have one frequency component where it is 2 pi fc minus fm. I have considered fc greater than fm, so it is fc minus fm. So one frequency is fc minus fm, the other frequency is fc plus fm. Now you see how after multiplication, how my frequency has translated. FM was my message signal, and now it has that message signal has now got translated to some frequency which is fc minus fm, and to another frequency which is fc plus fm. Okay, this is how the frequency translation takes place. Okay, so this is what we are doing, that so we get a message signal translated from lower frequency fm to higher frequencies, fc minus fm and fc plus fm. And this process is called the modulation. Okay, this is the modulation process which we do at the transmitting end. Okay, so a carrier signal CT is modulated. We call the message signal, we call it a modulating signal. Message signal is called the modulating signal. It modulates the carrier signal, and the resultant is the modulated wave. Okay, so that is how the modulation takes place. So mathematically, I have means just for a single tone in message, we have seen how that FM is translated to FC minus FM and FC plus FM. Now how you recover this signal? Because now the signal is changed. My voice is supposed to be from 0 to 3.4 kilohertz, but I am sending it at a very high frequency. Okay, it has been transmitted, and it has been received by the intended receiver. Now the receiver has to get it back to the lower frequency. Okay, it has to be translated back to the lower frequency. That is the modulation, demodulation process, just the opposite of modulation. So that demodulation process is by which the original message is recovered. Okay, and for that we multiply again the received signal. The received signal is ST. The modulated received signal is ST. ST is the product that we have got it here. So this ST is now multiplied again by the same carrier signal CT at the receiver. If I multiply it, now I get this. Okay, again you can check this one. Okay, you will be getting, if I multiply this, okay, if I multiply this with FC again, then one component will be FC minus FM, okay, plus minus FC, and another component will be FC plus FM minus FC. You can see that. Okay, so one is plus FC and another is minus FC. So you can just check it that basically again I am actually translating it back, okay, by multiplying. So what I will be getting, you can do it on your own. It is just simple trigonometric manipulation. If you do the simple trigonometric manipulation, you will see that after multiplying ST again with CT, one term will come like this, and the other terms, there will be two other terms, and that will be like this. Okay. Now you see, this is cos 2 pi fmt plus phi. This is the same signal, message signal. Okay. This is the same message signal which I had on the other side. Am cos 2 pi fmt plus phi was my original message signal. So you can see I have already got my mt. Only difference is that it is getting amplified. It is getting amplified by some factor. But that doesn't matter. I can always amplify it. I can reduce it by changing the gain factor and all these things. That is, it is just the volume will be more or volume will be less, like that. The volume of your sound. The volume of your sound will be more or it will be less. That's all. Okay. So it doesn't matter. But otherwise, it is the same message signal that has been recovered here. But what about these two components? These two components, I have to eliminate them. How I will eliminate them? I will eliminate them by passing the VT, this whole thing, by passing it through a low pass filter. Filter is what? Filter is again, it is an electronic device that can select certain frequencies and reject other frequency components. So when you give input to a filter, some of the frequency components will pass through that filter and some of the frequency components will not pass through it. They will be stopped. They will be rejected by that filter. Okay. You know, that's why the name filter. Filter will allow some part of the signals, some frequencies of the signal it will allow and some frequencies it will not allow. So low pass means it will allow only lower frequency. It will allow only lower frequency signals and it will stop higher frequency signals. Now you see, this one is very high frequency, 2 FC. FC is already very high. The carrier frequency is already high, and 2 FC minus FM. FM is very small compared to FC. So 2 FC minus FM is quite high. 2 FC plus FM, that is also very high. So these are very high frequencies compared to this one. This is only FM is the frequency. So when I pass VT through a low pass filter, the higher frequency, these two components, they are rejected. Okay, they are rejected, they are cut out by the low pass frequency. So accordingly, I have to take a low pass filter, and the low pass filter will have a cutoff frequency just more than FM. So it should be above FM. So it should not allow this. So that is the cutoff frequency. Means it, any frequency below FM, below this cutoff frequency will be allowed. Any frequency above this cutoff frequency will be not allowed in a low pass filter. So I take my cutoff frequency just above FM. So FM will be allowed. These frequencies will be not allowed. Okay. This is how the message is recovered. Now I am talking about a single tone message. So this can be now generalized to a multi-tone signal. As I was saying, that voice is having all the frequencies from 0 to 3.4 kilohertz. So there are many FMs. Basically, there are many sinusoids with different frequencies, and FM is 0 to 3.4 kilohertz. All the different sinusoids are there in my voice. So I can just, whatever the mathematical treatment we are doing it for one sinusoid, the same mathematical treatment is valid for all the sinusoids, because now my multi-tone signal is basically the addition of all the different sinusoids of different frequencies. Okay. So individually, if I do the same mathematical analysis for each and every sinusoid present in my message, I will get the same result. Every frequency will get translated to FC minus FM and FC plus FM. So accordingly, you can see that my message signal, this is by diagram I have shown it here, that if this is my original message signal spectrum, last class I have mentioned what is spectrum And in fact, today also I have already shown you the picture of spectrum. These are the spectrum. Here I have drawn the spectrum triangular. Here just arbitrarily I am drawing it. So here I am drawing it in this type of oval shape. Okay, this half ellipse I am showing. So this is my original voice signal. Okay, spectrum of my original voice message signal, which is from 0 to W. If it is my voice, then this W will be equal to 3.4 kilohertz. Okay, so this is the spectrum, and this spectrum now gets translated to Fc plus W is the maximum. Okay, so anything from 0 to W will get translated to Fc Fc plus W. All the frequency components from 0 to minus W, that's why mathematically we have to see all these things. So that's why actually we draw both positive side and negative side. So all these frequencies will now reflect here as Fc minus W. They will come as Fc minus W. The same mathematical treatment that we are doing. So we will be having the spectrum now looking like this. Okay, this is my original message signal spectrum, and after modulation the message signal spectrum will look like this. This is the positive frequency spectrum. This is the corresponding negative spectrum. Okay, negative frequency spectrum, the corresponding. Okay, and this is actually how we write it. The spectrum is written in this form. The spectrum will come as MF is the spectrum of the original signal. So that becomes now MF plus FC plus MF minus FC. This is how the translation taking place. Okay, this is MF plus FC and this is MF minus FC. This one is changed. Okay. Now this type of amplitude modulation. Now why we are calling it amplitude modulation? This because if you see this, okay, if you see here the amplitude of the original the amplitude of this signal by carrier signal, amplitude of the carrier signal is basically now getting modified as this. Okay, or if I see here, you see that what is my modulated signal? Modulated signal, my carrier signal was AC cos 2 pi FCT. After modulation, my signal becomes AC into MT cos 2 pi FCT. So basically the amplitude of my carrier is now modulated by the message signal MT. It is modulated means it is changed, modified by the message signal. It gets modified by the message signal. That's why we are calling it amplitude modulation, because the message signal is modifying the amplitude of the carrier signal, and thus the carrier signal is modulated. Okay, so that's why it is called amplitude modulation. This is the amplitude modulation, but and also the type of amplitude modulation here is called double sideband. Why double sideband? You see here, I was having actually one sideband here, 0 to 3.4 kilohertz. Okay, but now I am having something FC, whatever is FC, FC plus 3.4 and FC minus 3.4. So there are two sidebands, and the total length of this sideband now becomes 6.8 2W. Just check. Okay, so that's why we are calling it double sideband. Okay, this is one sideband and we are having two sidebands like this. Okay, that's why it is called double sideband. Suppressed carrier, we'll talk about why we are calling it suppressed carrier, because next slide I will show what is without suppressing carrier. Okay, so this is called double sideband suppressed carrier type amplitude modulation, DSBSC. Now this DSBSC type of amplitude modulation can be a bit modified if I include the carrier along with it. That means I don't do suppressed carrier. I don't do suppressed carrier. The carrier is there. Okay. If I do that, then you can see that one part of my signal AC MT cos 2 pi FCT and I multiply it with some factor Ka. So this was my earlier one, ACMT cos 2 pi FCT multiplied by Ka, some factor. Okay. So that gives you one part. And the other part, you see, it is just adding AC cos 2 pi FCT, the carrier. So basically what I am doing, I am multiplying my double sideband suppressed carrier signal, which I have got here. This signal I am multiplying with some factor Ka, and then I add the carrier signal to it. So I get this. What is this Ka? Ka is called the amplitude sensitivity of the modulator. And this type of modulation, we call it double sideband full carrier, because carrier is now here added. That's why that the previous one we are calling it suppressed carrier. This one we are calling it full carrier. And in fact, this is the general amplitude modulation scheme that we use. Now, here when I am adding the carrier, now this carrier when I am adding, obviously this will now require some extra power to be transmitted. Okay, compared to what I am transmitting here. Okay, the power required to transmit this, here the power required will be more, because it is having one term more, and that is the carrier signal that is also added to it. So I have to use some more power to transmit that carrier signal also. Okay, so that is a problem. Then why we are doing it? And that is the general amplitude modulation scheme. Why we are doing it? Why we are adding this carrier? If it is asking for more power, if it is demanding more transmission power, then why we do it? The reason is this. We'll see that. Okay, this is the pictorially I am showing it, how the waveforms look like. Okay, this is what the waveforms look like. This one I don't know where this picture has gone. This one is the double sideband. After double sideband, this one, the modulated wave will look like this. The carrier was some here constant AC cos 2 pi FCT, but now you see it has got modulated. The amplitude is modulated by some message signal. Amplitude is get modified. It is going up, going down like that, and that is due to the MT, the message signal. And now here you see the difference is, you can see this is my same message signal. Actually, I have used the same message signal, and this is the carrier signal. When I do double sideband suppressed carrier, the message would have looked like this, what I have shown here. This would have been the picture when I am multiplying them. When I am multiplying A with B, then I get the previous signal. But when I am adding this carrier with the DSBSC, now the signal will look like this. Okay, and this shape or this shape. Now this depends on my selection of Ka. If I take Ka small, then it will look like this. If I take Ka more, then it will cross over. It will cross over the zero line. It will cross over and it will look like this. This is for Ka more. Okay. Here I have written, instead of Ka, I have written mu less than 1, mu greater than 1. What is mu? It is related to Ka. As I said, if Ka is small, it is this. If Ka is big, then this is the modulated wave. What is Ka? How Ka is related to mu? Mu is basically equal to mod of Ka into M max. M max is the maximum value of your message signal at any time. Okay, this I don't know what will be the value. So whatever is the maximum possible value of your message, so that maximum possible value of your message signal into Ka, taking absolute value of that is my mu, and this mu is called the modulation index. So now you see, if you check here, if you check this, if Ka MT, maximum value of MT, if I take, then this becomes mu. Okay, so if that maximum value, this I am taking absolute value. So if that maximum value, absolute maximum value is positive, then it will become 1 plus mu. If that is negative, if it is the negative value, then it becomes 1 minus mu. So you see, the maximum value of SAM will become AC into 1 plus mu. That is the maximum possible value amplitude of SAM, and minimum possible SAM is AC 1 minus mu. Okay, just check it, because since I have taken the max Ka into maximum of MT as mu, so 1 plus mu, AC into 1 plus mu is the maximum possible value of S, and AC into 1 minus mu is the minimum possible S. So that is what I have written here, that SAM max is AC plus mu and SAM min is AC into 1 minus. This is the maximum value possible in this signal. This thing. So this is my AC 1 plus mu, and this is AC 1 minus mu. Maximum possible value of this one is AC plus mu, and minimum possible is AC into 1 minus mu. Now if I take mu less than 1, then obviously this minimum possible value will be always above 0. Okay, if I take mu greater than 1, then this minimum possible value will become negative. This way, if I take mu greater than 1, this one will become negative, and so this crossover will take place. So that's why I have written it here. Mu less than 1 will give you this, mu greater than 1 is this. Okay, so for mu 0 to, obviously 0 I will not take, because if I take 0, that means K is 0, that means there is no modulation. So obviously mu will be not 0. But if mu is taken to be maximum equal to 1, that is maximum 100% modulation, we have the upper envelope of the modulated signal wave always non-negative. Upper, that is what I have shown here in this picture. It is always non-negative. Okay. If it is non-negative always, then I can do a simple demodulation. I don't need to do all multiplication by carrier wave and all these things. I don't need. What I will do, whatever the message I have got, the modulated wave I have got, that modulated wave I pass it through a simple diode rectifier. You have studied diode rectifier, so you know what is diode rectifier. If I pass it through a simple diode rectifier, I will get the envelope of this. This will be the output. This will be the output. Okay. So that is why actually this amplitude modulation, as I have said, although it is using more power, but still it is used because the demodulation process is here less costly and simple. In the earlier demodulation process, what I had to do here, I have to multiply with a CT. So this CT has to be generated in a local oscillator. So I have to pay money for local oscillator. I have to do this multiplication. So this multiplication will be done by in a multiplier, which is also called mixer. Okay, which is also called mixer. So that mixer, again, I have to pay money for that circuit. Okay. Then I have to pass it through a low pass filter. So again, I have to pay money for that circuit also, because my receiver will here have three things: local oscillator, multiplier, and then a filter. So the receiver will become costly. Okay, receiver will become costly. Now this amplitude modulation was historically, it was developed and it was used for radio communication, and even today, other than the FM radio, this amplitude modulation is used in general radio broadcasting. Okay, this is used. Now, this is radio is used by all common people. Now, common people cannot pay. Some obvious, not all people can pay a huge sum of money to buy one receiver set. Okay, some people are there who are very poor, but they want to listen to the radio, because radio is something where you can listen to news and all these things. It is a very important gadget. Okay, it is not a luxurious gadget. It is an important gadget. So it is also the duty of the engineer to see that the system is such that it can be afford, a common people can afford that that gadget which is useful, which is not luxurious. Okay, so it is not a luxurious gadget. It should be used by any common poor people also. So accordingly, the engineers thought that we have to develop the receiver, we have to build the receiver in such a way that the receiver is less costly. Transmission, it can be costly because transmission is done by at the radio broadcasting station, which is owned by a government or some corporate, so it doesn't matter. But the receiver, the radio set at your home, that may be, then that may a poor person may have to pay money for buying it. So it has to be, you have to bring down the cost of it. And accordingly, this DSB SC modulation scheme was modified to this DSB FC type of amplitude modulation, so that we can do simple demodulation by using a simple diode detector. And hence the receiver circuit is simple and is low cost, which can be afforded by any poor common people. Okay, so that is the purpose. Okay, so this is the amplitude modulation scheme, DSB modulation and then amplitude modulation. Now this amplitude modulation, this both the types of amplitude modulation that which we have studied, we see that in both the cases what we are having is that original message bandwidth is W, but when I'm transmitting it, I have to use 2W bandwidth. Bandwidth is double sideband. One is double sideband full carrier, one is double sideband suppressed carrier. That's all. But other, so this requires more power for the carrier to be transmitted. This requires less power, but this one is easy to demodulate. Okay, but both of them is having that problem of double sideband. So the bandwidth is increased, the transmission bandwidth is increased. Okay, so that again has to be taken care of. If we want to take care of that, so what we can do, we can eliminate one of the sideband, because as you have seen that every time I was drawing like this, I was drawing this one symmetric. Okay, this side and this side, they are symmetric. So if they are symmetric, these two are symmetric. So if these two are symmetric, then why unnecessarily I send both the sides? I can send only this side, or I can send only this side, because other side is just a copy of this. However, this is only valid for a real signal, real valued signal. Complex or imaginary or complex signal, we will study about all those things later on. There are signals which are also complex, which are also imaginary signals. Okay, actually that is again mathematically the two signals can be combined in such a way that they form a complex signal. Okay, that is again mathematical. So that anyway, we need you need not bother about that. Right now we are considering that all the signals are real valued signals. So their amplitude are real values. Okay, so in a real valued signal, they are symmetric. This is not true in case of complex or imaginary signals. Okay, that you will see afterwards. For the time being, since the signal is considered assumed to be real valued, they are symmetric, and hence one sideband is just the copy of the other side. So we can transmit only one side of the double sideband. So only single sideband transmission is good enough. Okay, so we do single sideband transmission. How you do it? So accordingly select any one of the two sidebands, either the lower or the upper sideband. And how to select it? By band pass filter. We have to filter. Again, we have to select out only one particular band of frequencies and transmit only that sideband. Okay, this is called single sideband modulation. Okay, again single sideband modulation can be full carrier, suppressed carrier. Full carrier is good for your this envelope detection. Suppressed carrier cannot be used for envelope detection. Okay. Problem with SSB is that it requires filtering by ideal filter with sharp cutoff at FC practically, which is not possible. Again, if you see here, you see I need to do sharp cutoff. I have to cut this frequency exactly at this point, FC. Exactly at this point I have to cut. Okay. So that is the problem. I have to have a sharp cutoff from FC. Okay. The problem is practically the filters cannot be like that. I have drawn here that this is the practical low pass filter, pass band, stop band. But practically the low pass filter will have the frequency response like this. This is the frequency response, that how a filter should respond. Below FC, a low pass filter should give you output. Above FC, it will not give you output. Okay, but practically it is not so. Practically it will be giving you output till FC, it will give you output, but even after FC, for some frequency it will keep giving output, but at lower gain. Means it will be a bit smaller value. The value will be attenuated. Okay, it will be scaled down. The values above FC will be scaled down, but it will be there. It will be not exactly stopped. Okay, that is the problem with practical low pass filter. Similarly, this is a high pass filter. It is the pass band, but there will be some transition like this. Transition band will be there. Okay, you are ideally you should have a sharp cutoff like this, but practically you cannot design a circuit like this. You cannot build a circuit. Okay, because of the defined components, the resistor, capacitor, all these things used in the filter, they create this problem. Okay, this is the band pass filter. I want a sharp cutoff. So this sharp cutoff should be at FC, sharp cut, but practically you will not have. So something on the other side of the FC will also come into picture. Okay, although they will be suppressed a bit, they will be scaled down, but still it will be there. It is not exactly eliminated. So I have drawn here 4 types of filter: low pass, high pass, band pass, and this is called stop band or band reject or notch filter. You can see actually here it is just one particular frequency is stopped and other frequencies are allowed. So SSB may be modified. What we can do is that we want to go for SSB, but we can modify a bit by allowing or including a part of the adjacent side. Okay, although that is not useful, that is redundant, but we have to allow it. Otherwise, no way out, because SSB we cannot do sharp cutoff. Okay, and this type of modified SSB is called vestigial sideband modulation. Vestigial sideband modulation, and this is commonly used in TV transmission. The picture in the TV is transmitted using this VSB modulation. Here I have already said that why we go for SSB, because it uses large bandwidth, and large bandwidth is a problem in TV transmission because the picture in the TV transmission, the picture signal is a large bandwidth signal. Voice not a big problem, because voice you can see it is only 3.4 kilohertz. 3.4 kilohertz is nothing. Okay, compared to the large bandwidth that we have, the frequency spectrum that we have in nature, 3.4 kilohertz is nothing. Okay, whereas TV signal actually uses 5 megahertz. 5 megahertz, almost 1000 times of what our voice is using, more than 1000 times. Okay, so it uses 5 megahertz. So in TV, this is a big problem. If I go for double sideband, that 5 megahertz will require 10 megahertz of bandwidth to be transmitted. So in TV, we will like to have SSB, but as I have said that SSB sharp cutoff is very difficult, so we go for VSB, vestigial sideband modulation for TV transmission. So this is about the different types of amplitude modulation. Now the problem with amplitude modulation is that the amplitude modulation scheme is highly prone to noise. Any noise in the channel will affect your signal quality. Why? Because channel noise, they are additive in nature. That means they will always, whatever the signal is going, that signal, it will get added to the signal. It will add up. Okay. So if you see any signal, so when this signal is, this is the modulated wave, I am transmitting the modulated wave, this is the modulated wave, it is going like this. Okay. Now suppose at this point there is some noise, and because of that noise, this amplitude becomes like this. It gets added. It becomes like this, larger. Now when you demodulate, you don't know that whether it was the message or whether it is a noise. The amplitude has suddenly gone high like this. Then the amplitude is low. Again somewhere here because of noise, again the amplitude has gone high. Now wherever the amplitude is going high due to noise, you don't know. Means the receiver doesn't know that whether it is due to the noise or whether it was actually the message. So when it will do the demodulation, it will also take into account the noise, the rise in the signal due to the noise also. It will also add up that noise. It will not eliminate that noise because the receiver doesn't know that whether it is a part of the message or whether it was a noise. The receiver have no knowledge about it. So this noise, which is adding to the amplitude, and the amplitude is always fluctuating here. So you don't know if there is any fluctuation due to noise. You don't know whether that is due to noise or due to message, because the amplitude here is modulated or modified by the message. So you will, when you do the demodulation, your message, demodulated message, will also have the noise added to it. And that's why the quality of the signal after demodulation will be bad. Okay, that is the problem with AN. Okay, so what we do is that, means what is the other alternative is that instead of doing amplitude modulation, means instead of modifying the amplitude, why not modify the frequency or maybe the phase of the carrier signal AC cos 2 pi FCT. I modify the frequency of this, or I modify the phase of this signal, okay, carrier signal, because the carrier signal has to be modified. The carrier signal has to be modulated, and that modulation should be proportional to my message. Now instead, earlier what we were doing, we were changing the AC value, the amplitude. AC was multiplied with MT, and hence the amplitude was modified proportional to my message. But now I am saying that instead of modifying the amplitude, let us modify the frequency, because noise, I know, is adding. So what that noise will do, it will change the amplitude of the carrier signal. But the receiver knows that there is nothing to do with the amplitude. The message has nothing to do with the amplitude. So if at some point the amplitude is received to be high, then it will know that this is due to noise only, because the message has not changed the amplitude, because it is a different modulation scheme. So here the amplitude of the carrier signal is maintained constant, and the frequency or phase will be modified, modulated in accordance with the message. So that gives you a good immunity to the noise, okay, the signal. That's why you see nowadays we are using this FM radio, which is which you know is having a good quality, okay, good quality signal. Okay, you can hear a good quality music in FM radio. That's the reason. Okay, but there you have to pay something for it. When you are getting something good, you have to also pay for it. What is the cost you are paying for it? You have to pay the cost by increased bandwidth. The bandwidth is increased. Anyway, this bandwidth increased in case of radio transmission, voice, sound, audio, it's okay. I can go for it. As I have said that 3.4 kilohertz or even 20 kilohertz is nothing. So I can afford to go for higher bandwidth, okay? Because audio, in case of audio, it's okay. But for video, video transmission, again, we don't use FM. Okay, FM is not used. FM is used for the sound in TV, not for the video. Cannot be used because there it will be a problem. Because I have to sacrifice the bandwidth for a better quality in FM. Okay. Now what is this FM? Just these two equations will give you the idea how we are doing it. AC cos 2 pi FCT is my original carrier signal. In phase modulation, we just add a phase Kp into Mt. So you see this phase is added to it where the phase is proportional to the message signal. Okay. In frequency modulation, you just see what I am doing. Cos of 2 pi Fc plus Kf into Mt. So Fc is modified. Okay, the frequency is modified. So this is how we do the phase modulation or frequency modulation. Mostly frequency modulation is used. Phase modulation is not used much. Okay, and Kp, Kf are called the phase sensitivity and frequency sensitivity. Just these are some scaling factors. Okay, these are some, because Mt may be very large, so we don't want a very large fluctuation. Okay, so we just scale it down. So accordingly, we use this Kp, Kf scaling factor. And demodulation, I am not going into details of demodulation here, but the demodulation is mostly done by phase detector. So in a phase detector, there is a reference signal which is AC cos 2 pi FCT generated by the local oscillator, and this is what you are receiving it. So you just compare the phase of the reference signal and the received signal. You just keep on comparing the phase and you know that is the message signal. Similarly, using a phase detector also, you can find out what is the fluctuation in the frequency, because phase, you know, phase difference, whatever is the phase difference, if you do DDT of that, differentiation of the phase is your frequency. So DDT of phase difference is the frequency difference. So basically, using a phase detector, you can do both phase modulation and frequency modulation. Okay, because frequency and phase again are related to each other. Phase is integration of frequency, frequency is differentiation of phase. Okay. This is the picture, just the pictorially you can see it, that how the carrier signal, you see that it is constant amplitude, but with the message signal, the frequency phase here is changing and here the frequency is changing. There is slight difference. You can find it. Okay, you can see here when the signal is becoming lower and lower, the frequency is becoming smaller and smaller compared to my, so it is Fc minus something, whereas here it is Fc plus something. Okay, so frequency is modulated like this. This is the frequency modulation scheme. Okay, now coming to radio transmitter system, just some basic idea about that. Okay, just a basic idea about that is that I have, you can understand whatever we have said already. From there you can understand what we are doing. I have my audio signal source. So whatever source is there, from there some audio is generated. This has to be transmitted. So I will amplify it. I may do some noise removal or something. That is up to the broadcasting station to do. Okay, sometimes they mix, they add up this music from different instruments and all these things. All these things will be done. Then you're singing and all these things. All this processing is done. I have just put it in one block. So basically, it is the place where you are just adding up music from tabla, music from your violin, music from your keyboard. All these things are added up, and then again you have one amplifier. So these are some basic things you are doing, and then again you are amplifying. So basically, just to boost up the signal, you are amplifying. Here, this is the local oscillator, which is generating your this carrier signal, AC cos 2 pi FCT, and this FC is very high. FC is very high. In case of In general system, in general radio transmission, we have some electronic circuit where some high frequency of the range of megahertz, up to the range of megahertz, some high frequency signals can be generated. Okay, there are piezoelectric oscillators, there are many other oscillators, Colpit oscillator, Hartley oscillator, different types of oscillators are there. You will study about all those oscillators afterwards. So these are the oscillators which generate the signal. Okay. However, for microwave range frequency generation, for satellite communication, you have to have the frequency translation to microwave range, gigahertz. Okay, microwave range is gigahertz, 10 to the power 9 of that order. Okay, 10 to the power 9, that order, that is gigahertz. Okay, for microwave wave, we cannot use the general oscillators, the Colpit, Hartley, and all these oscillators which are made up of transistors, op-amp. They cannot be used. There, if it they are generally, we use for high power microwave cases, we use microwave tubes like klystron, magnetron, gyrotron. These are some microwave tubes. Or for low power application, we can go for some solid state oscillators which are made up of gun diode, pin diode. You will study about it afterwards, the details. So these are some microwave generators. Okay, so these are the local oscillators which will be producing your carrier signal. So your carrier signal, your audio signal, they are actually mixed up in this mixer, which is also will have a power amplifier, and then you will be having one antenna. In that antenna, you will be throwing away that modulated signal in space. I am talking about wireless communication. In wireless communication, you will throw it in the space. Otherwise, it will be transmitted through some other guided medium. What is an antenna? An antenna is a device that serves as interface between the electric circuit and space. So you have the electric circuit on this side, you have the space on the other side. The antenna is the interface. So antenna is used for throwing away the electromagnetic wave from this transmitter to the space, and in the receiver side, it is just the other way. It will take the electromagnetic wave from the space and put it in the electronic or electrical circuit in the receiver. Okay, and this the frequency that the antenna will catch, okay, or the antenna will transmit, that frequency, that will depend on how you have designed the size, shape, and the type of antenna. Okay, it will depend on it. So that's why you see there are different types of antennas. Okay, in your mobile phone you have a certain a particular type of antenna, although it is inside, you cannot see it nowadays. Walkie-talkie, you might have seen there is a small projection outside. In your car, you have one antenna, okay, to catch the FM radio when you are traveling. Okay, then your dish antenna at home, that is defined. Earlier days TVs, they used to use a different type of antenna called Yagi-Uda antenna. So these are all different types of antennas that are available, and that antenna design, the size and everything is based on the frequency range it is supposed to catch. Okay, generally an antenna will have, it is made up of some conducting metals, maybe of copper, but mostly aluminum. Copper is costly, so not all antennas are made up of copper. Mostly antennas you will see that they are made up of aluminum. Okay, and basically the antenna, purpose of antenna is to convert the electric current into EN in case of transmitter, or vice versa, that is electromagnetic radiation will be converted to electric current in a receiver. The simplest type of antenna is dipole. There will be two rods, okay, in the antenna. The antenna is made up of just a simple type. two rods. Okay, I think you might have seen that type of antenna in earlier times, just a few decades back. People used to have this portable TV at home with this type of antenna, having two rods. Okay, that is a dipole antenna. You might have seen that type of antenna. Okay, so that is a dipole antenna. Whereas the antenna that you see in your car, it is having only one rod. Okay, so it is a monopole antenna. Okay, and this monopole antenna is generally placed on a ground which is made up of a metal board. In your car, that roof of your car itself is that ground plane. Okay, and because that is made up of metal, so that's why we can use monopole in car. Okay, this monopole, actually it is something like this. In the, you have dipole antenna, means it is like you have positive negative. Battery is having positive negative two ends. Okay, so dipole is like that. Okay, monopole is something like you have one side, some batteries, you know, one side is grounded, the other side is positive. Okay, like that we can have that type of battery. So monopole is something like that. One side is grounded, the other side you are having the electric current produced from the other. It's like that. Okay, so we have these two types of simple antenna, although these are the basic types of antennas. Okay, dipole and monopole. Okay, a transmission antenna, what it will do, that whatever the electric current it is producing based on the modulated wave, because it has to throw the modulated wave in space. So whatever the modulated wave, whatever the fluctuating modulated wave is there, based on that that fluctuating electric current, based on that, you will be having some disturbance in the space. The radio, what is the disturbance? That is the radiation disturbance. Electromagnetic radiation will be there. Some electric field and magnetic field, fluctuating electric field and magnetic field will be produced in the air, in the space, by this antenna, due to this flow of electric current in the transmitter. Okay, so some current is produced here, some fluctuating electric current, and that electric current will be producing a fluctuating magnetic and electric field in the air, surrounding air, and that is how the EM radiation takes place in the antenna. A receiving antenna is just will do the opposite, that whatever the fluctuation electric and magnetic field is there in the air, due to that fluctuation, a voltage will be induced in the receiving antenna, and because of that induced voltage, the electric current will be formed, which will now flow inside the receiver. The receiver will pick up that signal. Okay, so it is electric current to EM wave and EM wave to electric current. Okay, what important parameter of designing an antenna is the directionality, in which direction. Okay, for example, the dish TV you have seen, which is on top of your roof, that dish TV is directed, and that's why you see that dish TV has to be placed properly, it has to be aligned properly with the satellite. Okay, because it catches the signal from the satellite. If you put the dish TV in the other direction, in any other direction, you will see that your signal is gone. Okay, so directionality is something which is very important. Okay, if it is a fixed system, generally and if we have just one-to-one, point-to-point communication. Okay, for example, that dish TV to the satellite is fixed, your dish TV, your house is fixed. Okay, so you have point-to-point communication between your home and satellite. So in that type of cases, we use the directional antenna. Okay, the antenna is designed to have the radiation pattern only directed in one direction. Okay, it is directional and it will be a unidirectional antenna. Whereas mobile phone, any mobile system, when you are having a mobile phone, you will keep on moving here and there, and your direction to your mobile phone will be picking up the signal from the nearest base station. Nearest base station. You might have seen the base stations which are placed on the rooftop of some buildings in your locality. Okay, those are the mobile base stations. Okay, so those base stations, the direction of that base station will keep on changing when you are moving. Okay, so in that type of systems, you cannot have a directional antenna. So there is we will be having a non-directional antenna, which is generally an omnidirectional. We call it omnidirectional, all in all directions. Okay, so it can radiate EM wave or it can receive EM wave uniformly from all directions. Okay, these are the different types of antennas you have. Okay. So this up to this I'm completing today. Okay. So we'll continue from here the radio receiver system and other things tomorrow. Okay. Because tomorrow is a working day, means you have class tomorrow. We are following the Friday timetable. So tomorrow again we will be meeting at 5 p.m. Okay. I have posted these slides. Okay, already I just some time back I have posted these slides. So you can look into the slides. Okay, and because your exam is coming, I think next week is your exam. So I think right now you can start studying about it, about this course. I will try to finish up this course by Monday. I'll try to finish it up. Although next Friday is your last working day, last lecture day, but I'll try to finish it up by Monday. And next Friday, I will take one small quiz. Okay, small quiz, objective type. Okay, and as I have already said, no big mathematical calculations, mathematical derivations are required. I have given all those mathematical relations and everything just for your understanding. But small mathematical relations you should remember. Okay, you must remember. For example, if I say if the KDR frequency is this, and if my input signal frequency is this, then what will be the frequency of my modulated wave? If I ask this type of question, you should be able to answer it. Okay, these are very simple, calculations. I will not ask any big calculations or any complicated calculations. Okay, but some small basic things I may ask. Okay, otherwise the whole part of my course is story time. Okay, so you go through the slides, read the things, okay, and try to know the things. Okay, and in your quiz I'll be asking this type of small objective type of questions. Okay, so that's all for today. If you have any question, you can ask me right now, or maybe tomorrow you can ask me. Okay. Bolo. Any question you have? If not, then you can leave the meeting.